As you descend from a warm sea surface, the water can suddenly turn cold across only a short vertical distance. Nothing solid blocks the way, and no visible line must appear in clear blue water. Yet skin registers a boundary that instruments trace as a steep temperature change with depth. Above it, waves have stirred a relatively warm surface layer beneath sun and wind. Below it, colder water resists mixing upward because density generally increases as seawater cools. Transition between them is the thermocline, a physical gradient rather than a separate substance. Swimming through it feels like entering another water mass, but the boundary itself is continuously moving. Storms can deepen it, calm sunlight can sharpen it, and tides can lift or lower it along coasts. Its depth may change while a diver remains nearly stationary, producing alternating pulses of warmth and cold. The mystery lies in how an invisible temperature slope organizes sound, nutrients, oxygen, and animal behavior. Each meter downward changes pressure slightly, but pressure does not cause the abrupt chill felt across a shallow thermocline. Instead, solar heating enters from above, while turbulence decides how deeply that heat is mixed. The resulting profile records a contest between buoyancy, stabilizing layers, and motion trying to overturn them. A swimmer crosses the outcome directly, but sensation alone cannot define its depth or strength. To understand what you feel, the investigation must descend through seasons, latitudes, weather, and living responses. Sunlight warms the upper ocean most strongly because radiation is absorbed as it penetrates water. Wind and breaking waves mix some of that heat downward, often forming a surface mixed layer. When turbulence weakens, warm, low-density water remains above colder, high-density water, and stratification strengthens. The thermocline occupies the zone where temperature decreases most rapidly between those more uniform layers. In tropical oceans, a strong permanent thermocline can persist beneath a warm surface throughout the year. At temperate latitudes, seasonal heating often builds a shallow thermocline in spring and summer. Autumn cooling and stronger storms can erode that seasonal structure, deepening the mixed layer. High-latitude profiles differ because cold surface water, ice processes, and salinity can complicate the density pattern. Temperature, therefore, cannot describe every stable ocean boundary without considering dissolved salts. A halocline is a steep salinity gradient, while a pycnocline is a steep density gradient. Thermoclines and pycnoclines often overlap, but salinity can strengthen, weaken, or even reverse temperature's density effect. Fresh warm water over saltier cold water may be exceptionally stable despite active waves above. Temperature probes, lowered through the sea, directly record the gradient, rather than relying on human sensation. A conductivity temperature depth profiler measures temperature and salinity, while pressure indicates sampling depth. Thermistor chains record changes at fixed levels, revealing the boundary rising, falling, and breaking through time. Autonomous gliders repeat sloping descents across large areas, trading fine local detail for broader coverage. Acoustic instruments can detect biological layers influenced by stratification, though sound does not measure temperature unambiguously. These methods show that the thermocline is a zone with thickness, not a perfectly thin sheet. They also reveal internal waves traveling along density boundaries beneath ordinary surface waves. An internal wave can displace a thermocline by tens of meters without producing an equally dramatic surface crest. As it passes, cold deep water rises, then falls, changing local habitat over minutes or hours. Verified observations establish temperature structure and motion, while biological consequences require separate behavioral evidence. The descent now reaches a boundary that is physically measured but ecologically variable. One common explanation treats the thermocline as a wall preventing all exchange between surface and depth. Stratifications suppresses vertical mixing, but it does not stop molecular diffusion, animal movement, storms, or turbulent events. Nutrients regenerated below can cross upward through mixing, upwelling, and boundary disturbances. Oxygen can cross downward from surface contact and photosynthesis, while respiration consumes it within deeper water. The thermocline therefore regulates exchange without sealing the layers apart. Another oversimplification assumes the coldest sensation marks the deepest or strongest gradient. Human skin adapts, currents move across the body, and local patches can distort what a swimmer perceives. Instrument profiles may show multiple steps created by intrusions of water with different temperature and salinity. Fine layers can form, merge, or overturn, giving the boundary a staircase rather than one smooth slope. Double diffusive processes may develop where heat and salt contribute opposing density tendencies. Such structures are physically plausible and observed in suitable settings, but not every stepped profile shares one cause. Internal tides provide another explanation for rhythmic thermocline movement near slopes and continental shelves. Tidal flow crosses topography, displaces stratified water, and launches waves along submerged density surfaces. When those waves steepen or break, they generate turbulence and transfer energy into mixing. A sudden cold surge on a reef may therefore come from displaced deep water rather than regional surface cooling. Repeated timing with tides supports that interpretation, while a single cold pulse remains ambiguous. Plankton patches can accumulate along density gradients because swimming, buoyancy, and converging flow limit their vertical spread. Acoustic scattering may outline those patches, but the echo marks organisms, not the thermocline itself. Fish can gather near the gradient to exploit prey, or remain within preferred temperature and oxygen ranges. Their aggregation does not prove they detect temperature alone, since food and light also change with depth. Some predators cross the boundary repeatedly, accepting cold exposure when prey rewards exceed metabolic costs. Others track a narrow thermal range, moving vertically as internal waves carry that range upward and downward. These Q-action sequences are documented through movement and environmental records, but motivation remains interpreted. Strong stratification can also support a subsurface chlorophyll maximum near the meeting point of light and nutrients. Higher chlorophyll indicates pigment concentration, not automatically faster photosynthesis or greater edible biomass. Sampling time matters because the thermocline may shift between a biological observation and a temperature profile. Limitations increase near steep terrain where a boundary can vary substantially across short horizontal distances. The thermocline shapes life by dividing warm illuminated habitat from colder, often nutrient-richer water beneath. Phytoplankton above may exhaust nutrients when persistent stratification prevents rapid replenishment. Cells that sink toward the gradient encounter more nutrients but less light, creating a narrow zone of compromise. If you follow a diving seabird, its prey may concentrate near that same compromise layer. Small fish detect prey density, enter the layer, and school where feeding gains exceed thermal costs. Tuna encountering cold water may turn, slow, or make brief excursions depending on species and body condition. Marine mammals maintain internal heat and can cross strong gradients while hunting at depths inaccessible to many fish. Coral reefs near internal wave paths can receive cool nutrients and plankton from deeper water. The same pulses may temporarily relieve heat stress, although they can also expose organisms to low oxygen or corrosive conditions. Aquaculture cages intersecting a moving thermocline may experience abrupt changes in temperature and oxygen. Farmed fish cannot always leave, turning a natural oscillation into a health and management concern. Submarines and sonar operators care because temperature structure changes, sound speed, and bends acoustic paths. Sound can refract away from receivers, creating shadow zones where detection becomes difficult. This effect is calculated from measured profiles, not evidence that the thermocline blocks sound like a wall. Divers face practical consequences when cold increases breathing demands, reduces dexterity, and accelerates heat loss. Storm-driven mixing may erase a shallow thermocline while bringing nutrients upward and surface heat downward. This sequence can reduce surface temperature, alter plankton growth, and change where fish gather. Climate warming is increasing upper ocean heat in many regions, often strengthening or extending stratification. Responses vary because winds, freshwater input, currents, and regional circulation can counter or amplify warming. A changing thermocline can alter nutrient supply, oxygen renewal, habitat compression, and exposure to marine heat waves. Future evidence requires continuous profiles because isolated casts cannot resolve boundaries moving with internal waves. Long thermistor records can separate tidal oscillations from seasonal deepening and storm disruption. Repeated glider sections can show whether a changing profile reflects local weather or a broader water mass shift. Predators should repeatedly alter depth when prey positions and thermal limits shift together across the gradient. Community differences above, within, and below the gradient must remain consistent before separation is inferred. Turbulent exchange must be quantified rather than assuming total isolation from stable density alone. If you descend through the opening image again, the first cold touch may arrive higher than before. An internal wave may lift the boundary, a storm may deepen it, or fresh water may sharpen its upper edge. The water remains continuous, even as temperature changes fast enough for skin and instruments to agree. Above, sunlight and wind continually rebuild the mixed layer that made the contrast possible. Below, cold water stores nutrients and heat histories shaped by circulation beyond the swimmer's view. Across the gradient, Particles sink, animals migrate, sound bends, and turbulence occasionally opens brief passages. No single depth defines the thermocline across an ocean, a season, or even one moving afternoon. The boundary is directly measurable, but its ecological meaning depends on salinity, oxygen, light, flow, and behavior. What feels like a hidden wall is scientifically a shifting thermal gradient, permeable to life and never fully still.